The Double Slit, Actually Science, Episode 3. Chapter 1. The Setup. The double slit experiment is the most conceptually disturbing experiment in the history of physics. It has been run in many forms over 2 centuries, and it still has no satisfying explanation. That is not a failure of human understanding. It is a feature of the universe. The setup is simple. Take a solid barrier and cut 2 narrow parallel slits in it. On one side of the barrier, place a source that fires particles, electrons, photons, atoms. It works with anything quantum. On the other side, place a detector that records where each particle lands. Fire the particles one at a time. Each particle hits the detector in one specific place and leaves a single mark. If particles behave like the tiny balls of classical physics, with definite positions and trajectories at all times, you would expect each particle to go through one slit or the other. Over time, the marks on the detector should accumulate into 2 clusters, one behind each slit. Simple, sensible, classical. That is not what you get. What you get instead is an interference pattern, alternating bands of many marks and no marks spread across the entire detector, not 2 clusters. Stripes. This is the pattern you would expect from waves, not particles. When waves pass through 2 slits, they spread out on the other side and interfere with each other. Where 2 crests meet, the wave is amplified. Where a crest meets a trough, they cancel. The result is an alternating pattern of intensity. The particles are producing a wave interference pattern, but you are firing individual particles one at a time. There is nothing for them to interfere with. There is no other particle to interact with. Each electron or photon or atom travels alone from the source to the detector. And yet somehow each particle contributes to an interference pattern. As the marks accumulate, the pattern emerges. The particles are avoiding certain positions on the detector, the positions where destructive interference would occur if waves were coming through both slits, and preferentially landing in positions where constructive interference would occur. Each particle, individually, is behaving as though it went through both slits simultaneously and interfered with itself. This is not a malfunction of the detector. It is not a calibration error. It is not an artifact of the specific particles being used. The experiment has been repeated with electrons, photons, neutrons, atoms, and molecules containing dozens of atoms. It works every time. Each quantum particle, when it encounters 2 slits, does not choose one slit. It travels as a wave through both slits, interferes with itself, and then collapses to a single point on the detector. The natural question is, fine, but which slit does it actually go through? This is where the experiment becomes truly disturbing. Chapter 2. The Measurement Problem. The obvious next step is to put a detector at the slits, a small instrument that can tell you which slit the particle went through without stopping it, just measuring it. When you do this, the interference pattern disappears, completely, immediately. You get 2 clusters on the detector, one behind each slit, exactly as classical physics would predict. The particle, when observed at the slits, picks one slit and goes through it. When not observed, it goes through both and produces an interference pattern. When observed, it picks one and produces 2 clusters. This result is what physicists call the measurement problem, and it has resisted satisfying explanation for nearly a century. It is important to be precise about what observation means here, because the popular version of this experiment often gets it wrong. The disturbance caused by placing a physical detector at the slits is not what destroys the interference pattern. You can design detector systems that interact with the particle so gently that any mechanical disturbance is far too small to account for the change in behavior. What matters is not the physical disturbance. What matters is whether information exists, anywhere in the universe, about which slit the particle used. If the detector stores information about which slit, even if no human ever looks at it, even if the information is immediately erased after being recorded, the interference pattern disappears. Physicists have spent decades designing increasingly clever experiments to probe this boundary. In delayed choice experiments, the decision of whether to measure which slit the particle used is made after the particle has already passed through the barrier. In some versions, the measurement is made or not made after the particle has almost reached the detector. The particle seems to retroactively adjust its behavior based on whether a measurement was going to be made. In quantum eraser experiments, the measurement information is collected and then destroyed before it can be read. When the information is successfully erased, the interference pattern returns. When even a single copy of the information survives somewhere in the universe, the interference pattern is gone. The experiments are precise, well replicated, and deeply strange. The conclusion they point toward is this: a quantum particle does not have a definite position or trajectory until a measurement forces it to acquire one. Before measurement, it exists in what physicists call a superposition, a combination of all possible states, each with a certain probability. The act of measurement collapses this superposition into a single definite outcome. Why does measurement do this? Nobody knows. What exactly happens during the collapse? Nobody knows. The mathematics predicts the probabilities perfectly. The mechanism behind the mathematics remains one of the deepest open questions in physics. Chapter 3: What it means. Richard Feynman said that nobody understands quantum mechanics. Feynman did not say this as a complaint. He said it as a precise description of the situation. He was one of the physicists most responsible for developing and applying quantum mechanics to practical problems. He received the Nobel Prize in Physics in 1965 for his work on quantum electrodynamics, one of the most precisely tested theories in all of science. He understood the mathematics more deeply than almost anyone alive. He still said nobody understands it. What he meant was this: the mathematics of quantum mechanics is extraordinarily successful. It predicts experimental outcomes to 10 decimal places. It underlies every transistor, every laser, every modern electronic device. It works. It works better than any other theory in the history of physics. But the mathematics describes a world that does not match our intuitions about what is real. Particles do not have definite positions until measured. Multiple possibilities coexist simultaneously. The act of observation changes the thing being observed. Information seems to travel instantaneously in certain situations, in apparent violation of relativity. The question of what the mathematics is actually describing, what physical reality looks like at the quantum level, is called the interpretation problem, and physicists have been arguing about it since the 1920s without reaching consensus. The dominant interpretation, called the Copenhagen interpretation after the city where Niels Bohr and Werner Heisenberg developed it in the 1920s, says roughly this: before measurement, a particle exists in a superposition of all possible states, each with a certain probability. The wave function is a mathematical description of this superposition. Measurement collapses the wave function, producing one definite outcome chosen according to the probabilities. This interpretation is instrumentally useful. It tells you how to calculate the right answers, but it deliberately avoids asking what is actually happening before measurement. Bohr famously said that it was meaningless to ask what an electron is doing when you are not looking at it. Alternative interpretations have been proposed. The many worlds interpretation says the wave function never collapses. Instead, every measurement causes the universe to branch, with all possible outcomes occurring in different branches. Pilot wave theory says particles always have definite positions, guided by a real wave. Relational quantum mechanics says quantum states are only defined relative to observers. None of these interpretations has been experimentally distinguished from the others. They all make the same predictions. The double slit experiment produces the same result in every laboratory, with every type of particle in every country at every time. The interference pattern appears when unmeasured, it vanishes when measured. This is not going to change. What it means about the nature of reality is something physicists are still figuring out.